Hello there, Mr. Chen here for Algebra 1. About to start a lesson. Please grab your student companion and turn to page 123. We're about to do 6-3, Exponential Growth and Decay. Let's start with the opener here. Cindy is buying a new car and wants to learn how the value of her car will change over time. Insurance actuaries predict the future value of cars using depreciation functions. One such function is applied to the car whose declining value is shown. So the word depreciation and the word declining means to go down. Question A, describe how the value of your car decreases from year to year. Take a look at what's going on in this table. We have year 0, 1, 2, 3, and 4. The values themselves start dropping from year to year. That's the nature of a car ownership. We actually lose 1,480 the first year. From the first year to the second year, we're actually going to lose about $1,307. From the second year to the third year, we're going to lose 1,113. And from the third year to the fourth year, we're going to lose about $890. All right, describe how this is. This is not linear. The amounts that we lose are not the same. So this is considered to be non-linear depreciation. What kind of function would explain this type of pattern? This is called exponential decay. The name of this section is called growth and decay. Growth means things are increasing. Decay is where things are decreasing or declining. All right. Next question. Given your answer to part B, what is needed to find the function the actuary is using? And by the way, the word actuary is just a fancy person who does statistics or statistician. Well, we would need to know how much the car costs. Year 0 is the most important part. That's called the initial value. Initial means the starting value. And even though it's nonlinear, it goes down by a certain percentage. That's what's happening each year. It's called the percentage of depreciation. What is the constant ratio for the declining value? Now, constant ratio is referring to how it is affected by this number. So we do start at 100% initially. Our constant ratio, because it's going down, is somewhere between 0 and 100%. Make sense? I mean, that's kind of obvious. So here is referring to between those two numbers. All right. Let's take a look at the next page. Any questions? Nice. So our original opener is about decay, how something loses value like a car when you buy brand new. We have other situations where things actually grow. And before we do that, let's talk about the parts of these exponential growth and decay functions. In the upper left-hand corner, write down exponential growth. There's really nothing too different between growth and decay, except that the value of it either makes it bigger or smaller. So in this case, growth means that our percentage is greater than 100% when we manipulate the initial values. Make sense? Right? Goes up? Okay. So let's create a function here. It's called an exponential growth function. We'll use f of x. Now we all know that as y. Not a big deal. Equals to, we're going to start somewhere. Well, let's use the letter a. That represents the initial value. Kind of like in the opener, we had $10,000 for the car, right? Then we're going to multiply this initial value by a percentage. This percentage we're going to call the base, or b. B is the constant ratio. All right, that's it. Brought to a power. Interesting. This power is usually referred to time per year, per 2 years, for 3 years. Each time, like the opener, the car decreases its value. It went to year 4. So that power would be to the 4th, or actually to the 3rd power. Let's see. Yes. All right. Now, when it comes to growth, the base literally means greater than 100%. So this function, f of x, equal to a times b, I can break it down a little more, is literally 1 plus r. The 1 is 100%. R is the growth rate. Oh, forgot the power right there. Okay, the power is time. Just a reminder of that. R is the growth rate. You do need to convert it to a decimal in order for this formula to work. Notice 100% is literally 1.00. Okay, so I'm not going to jump to the note taker's actual problem until later. I'm going to use a book, the example in the book. Example 1, here we go. We're going to talk about population of a city called Hillville. The population, you can shorthand it POP apostrophe L, of Hillville grows at an annual rate of 15%. That's pretty fast. What is the population after 5 years? They do tell you one other piece of information. That is the initial value of the actual population is 5,000. That's in the book. All right, we need a formula. Here we go. F of x equals to a times 1 plus r to the x power. We know our initial amount, a is 5,000. Very good. Let's put that in. There's our growth, 100% plus, ooh, 15%. That's your R value, your growth rate. We got to convert 15% to 0.15. And we're going to do this for 5 years. Make sense? We're just finding f of 5. Oh, that's function notation, by the way. It doesn't mean f times 5. It just means f of when x is 5 years. Let's punch that into a calculator, because I'm sure most of us can't do this by hand. You are allowed a calculator on the test or final. So grab a calculator if you don't have one. Just follow along with me. Okay. Our formula is 5,000 times parentheses 1 plus 0.15 close parentheses to the power of 5 years equals, wow, 10,056.78594. Let's round out to the nearest person. Let's write that down. Nice to have some technology, huh? There's your answer. Not too bad, right? Yay. Let's take a look at the example in our note taker just to practice a little more. Here we go. The population of Valley Town is also 5,000 with an annual increase. And by the way, annual means every year, okay? Yearly. So I'll let you know that. Annual means yearly. Forgot to mention that earlier. That means yearly. Over here to Valley Town, they also have 5,000 people with an annual increase of 1,000. Holy cow. Can the expected population for Valley Town be modeled with an exponential growth function? Explain. Now this is kind of weird. Doesn't tell you that it's a percentage, but it's going up by 1,000 people. That's crazy. So we have, what, 5,000 people to start with? Then we add 1,000. That gives us the 6,000. Add another 1,000, and so on and so forth. Ladies and gentlemen, this is not exponential. This is considered linear. That's what's going on here. Exponential is when you have a percentage increase. It's not exponential growth, it's linear. Still a lot though, right? Still a lot. All right. I mean, think of the graph of Hillville. You're increasing 15% every year. That's a sizable chunk there. When you're adding a percentage on top of a percentage, I mean, think about the graph of this. If we were to graph number example 1 on the left, we would get something like this. Like that. Whereas the graph for a linear function looks like this. Kind of like this. Okay. Makes sense? All right. Not too bad. Any questions about this? All right. Let's jump to something else here. Example 2. exponential models of growth. What will be the difference after 15 years if the interest is compounded semi-annually rather than quarterly? Okay, there's not a lot of information right here. What are we talking about? We're talking about money. Sometimes these note takers don't tell us everything. So we're going to use a similar equation, the exponential growth function, but it's called compound interest. Write this down on the left. You may have a bank account locally that your parents started for you. And what we're going to do is explore this thing called a compound interest formula. And the parts of it are very similar to the exponential growth function up there, okay? All right, here we go. A equals, that's like f of x. P, your initial amount, times 1 plus r over n to the nt power. Okay, we have a power, we have the 1, I mean, it looks familiar, right? That looks like 100%. We're growing money here. We are growing money, 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 money. A is the final amount. P is the initial amount, also known as the principal. Principal, in this case, is the initial amount. Okay. R is the annual interest rate. T is time. N shows up in two places. It's the number of times interest is compounded per year. So this is a formula, basically. You just have to follow it to get the right answer. Typically, a local bank compounds interest 12 times a year. Yeah, that's called monthly. There are 12 months in a year. Over here to the right, we have an interesting situation where they say, hey, what would the difference after 15 years if the interest is compounded semi-annually rather than quarterly? Semi means half of a year. Yeah, makes sense? Half of a year. How many halves are there? In this case, the answer is 2. If we use the formula, it would be n equals 2. Quarterly means we take a year and chop it up into 4 quarters. That's what quarterly means. N equals 4 here. Is there a subtle difference between quarterly versus semi-annually? Now, just to give you a little history here, the information given to us in this book is we have $1 million, let's just say. And let's just say with its compounding interest at 8%, annual interest. And I pick 1 million because it's just a simple number to just compare, okay? And 8% when you convert it to a decimal, of course, is 0.08. That's your R value, folks. Let's just plug into the formula with both scenarios. Is there a difference when you're trying to compound interest semi-annually versus quarterly? So I'm using the formula, compound formula on the left. So here, let's write it a little small. I apologize. A equals 1 million times 1 plus 0.08 divided by, in this case, 2 to the power of 2 times 15 years. Okay, that's the time now. 2 is the, let me use a red color here so you can kind of see that. Oops. And in this case, time is 15 years. And I'm going to punch this into the calculator in a moment, and we're going to do it with also quarterly. Same percentage rate, 8%, but this time we're dividing by 4. We're calculating 4 times a year. Do you get a lot more? I don't know. What's your thought on that? Okay, I'm going to punch in both scenarios right now into my calculator. Here we go. 1 million bucks times parentheses, use parentheses, 1 plus 0.08 divided by 2, close parentheses to the power of, 2 times 15. I get this wacky, crazy number. Woo! That's a lot of money. Okay, let's copy that over to our notes. Wow. That's a lot of dough there. 15 years, your $1 million investment goes to $3,243,397.51. Wow, lot of money. What happens if we change the problem, make it divide by 4 because of the semi-annual, right? Let's try that one. It's not a complicated calculator. I'll just have to type this in again, no big deal. But this time we divide by 4. And it's 4 times 15. Whoa, a little more money, but not as much as you thought it would be, right? The reason why is because we're breaking up the interest rate brought to a power. This answer, $3,281,030.79. Not much more. It's about $37,000 more. Yeah, not as much as you would have thought. Okay, next question in example 2. Any questions, please ask. This is all about money, putting money in the bank and see how much money it makes after so many years. This is basically interest on top of interest, right? You don't take the interest out. If you make some money after a year, you leave it in your account. And when you do another calculation, the second year, you're making interest on the money you initially put in and the money you made from the previous year. It's called compounded interest. All right. Second question, B, what would be the difference in after 15 years if the interest rate is compounded monthly rather than quarterly? Okay, so they're just asking for one more calculation. We're going to change n equals 4 now to n equals 12. Is it going to be a lot more money? Let's take a look. $1 million is a great place to just compare the numbers with the previous ones. And our n value is 12 this time, yeah? For 15 years, that's a long time. Most of you will probably be 28, 29 years old by then. You gotta be patient though to make money, right? But it's doable. It's definitely doable. Let's punch out in the calculator. Any guesses what that would be? Okay, so we have $1 million times parentheses 100% plus 0.08, but this time we divide by 12. See that? See that number right there? 0.06 to the power of, this time the same, 12 times 15. Okay, a little more. Let's go back to our notes here. How are we doing out there? Not too bad, huh? Money's money. $3,306,921.48. Okay. All right. Any questions about the money we're making? All right. We're going to skip the habits of money and jump to example 3. Well, we've talked about exponential growth. We've talked about compound interest money. And now we're going to go to the opposite of compound exponential growth. We're going to go to exponential decay. Decay when you're losing numbers. We're going to use the same function again. F of x equals a times b to the x with the base, right? But instead of adding a common ratio, we're now going to subtract a common ratio or rate. So the formula is just either adding r or subtracting r in this case. This is considered decay. We still have that 100%. We still have the initial amount A. But let's see what happens in this scenario, okay? Suppose the number of views, I think we're talking about video views on TV, decreases by 20% per day. Oh, that's sad. You're losing your audience, right? Oh, no. In how many days will the number of views per day be less than 1,000? I mean, we can set up the equation, f of x equals to a times 1 minus r to the x power. So the initial value that's not listed here, and I apologize, sometimes you have to pause and think about, oh, what are they referring? This is in the book, by the way. Right now there are 8,192 views the first day. So that's our initial value, A value, okay? So that goes into the spot right here. Are decreasing 20% per day. 20% must be converted into a decimal. That's 0.20 when you move it 2 spaces to the left. So my R value is 0.20 to a power of x. Inside there, 8,192. Oh, 1 minus 0.20? Interesting. That is 0.80. Let's think about that for a second. We don't want 100%. We only want 80% of yourself each time, every year. You're going down 20%, but you're 80% of your value. This is the base, folks, which is 80%, okay? Makes sense? Now, we in Algebra 1 need to figure out how many days it takes. I'm sorry, yeah, in this case, x, before it hits below 1,000 views. We kind of have to manually solve this. We can solve it in Algebra 2 in a couple of years for most of you. But right now, I'm going to write down 0, 1, 2, 3, ... Okay? You have to manually punch this in the calculator. First day, of course, we know is 8,192. 80% of that drops it down to this number. So on the calculator, this number that I have right here is 6,553.6, okay? Let me show you how that works. Let's just count, right? Day 0, right? Oh, I don't know why it's called first day. That should be like the 0th day, right? I'm gonna do that. Okay, day 0. Let's switch over to our calculator, and we have 8,192 views on the first day times 0.8. Bam. Okay, that's 1. Times another 0.8. 2. Are we below 1,000 yet? So we're manually using our calculator to check this out, okay? Let's keep multiplying. It's 3, 4, and so on, 5, 6, 7, almost there. It's kind of slowing down. Oh, almost there. Ding, 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 ding. All right. So that took 10. 10 clicks. Ladies and gentlemen, that gives me a number of 879 views. Sad for that YouTuber, I'm guessing, right? All right, that's your answer, 10. Ha, 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 ha. Next page. Okay. I was looking at this example earlier, example 4. I think there's a typo. The name itself for example 4 is Exponential Models of Decay. And I realized I may not have noticed this last year when I did this. Let's read along as I read aloud. How would the average rate of change, and by the way, rate of change means slope, over the same intervals be affected if the population increased at a rate of 8%? See that? Decay increased, probably a typo, decreased. Eventually this town is going to be a ghost town. Now initially, you start with a certain amount, right? And you lose 8%, it's going to go like this probably. Boom. Let's just say 5 years, right? You lose 8%, fine. This is your population here. But the next 5 years, 8% of that, 8% of a smaller number makes it look like this. Let me do this again. It's kind of hard to see. So let's just do that, make it a little steeper. 8% of this is not as steep. And so on and so forth, right? 8% of smaller and smaller numbers has a less steep slope over time. This, ladies and gentlemen, is called an exponential decay function. So here, slope, if you were to use y2 minus y1 over x2 minus x1, you'll find that the average rate of change slows down, as you can see by the graph. Assuming that they made a typo, instead of increase, it should be decreased by, okay? All right, let's take a look at number 5. We're gonna skip number 5. Let's jump to the last page, woohoo. Okay, so this is just pure calculation by knowing what to plug into those formulas. We're going to look at either a growth or decay function. Here are the equations again. Y or f of x equals a times b to the x. Let me zoom in one more so I can see it better. Very good. B is based off of either 1 plus r or 1 minus r. I'll put a little plus or minus. A, of course, is the initial value. Yeah? All right, let's take a look at number 5. The initial value of 100, fine. Let's put that in, 100, that's my initial value, times 1 plus, oh wait, oh, increase, that's a plus of 5%. Convert 5% to a decimal, 0.05, very good, to the power of x. Yay, clean that up. Add those two values there. Your function is 100 times 1.05. That's literally 105%, by the way. That's what that means, okay? Easy peasy. Any questions? Okay. Next problem. Another increasing. Wow, okay. It's pretty much the same as number 5. 1,250. Ooh, 25%. 2 decimal places, right? Careful there, right? 0.25 to the x power. Rewrite that a little bit better. That could be money, it could be a number of people in the town. But there it is, my exponential growth function. Nice. Ooh, decreasing is next, thank goodness. I was getting a little bored there. Decreasing this time. 50%. 0.5. Let's use the function. 512. But this time, you know, 50 is kind of boring. I remember seeing that last year. Let's change that 50. I'm not too fond of the number 50, yeah? Let's change it, yeah. Let's call a decreasing rate of 47%. That's more like it. Something more interesting. 50, yeah, whatever. Here's the reason why. When I put in 1 minus 0.47, by the way, 0.47, subtract that from 1, I'm going to get this answer. 512 times 0.53 to the x. I want 53% of the original. 53% of the original is the same as 47% decrease. Make sense? Because it always adds up to 100. All right. Not too bad. Let's jump to number 8. Oh, another decreasing problem. Nice. 12%. 0.12. Let's plug this function in. 10,000 is my initial value times 1 minus 0.12 to the x power. Okay, clean that up. Ooh, 1 minus 0.12 is 0.88. That's 88%. And when we'll be done at this point, I'm going to put a what if question for a secondary part, because let's make it a little more interesting, yeah? Gets a little boring after a while doing the problems 4 times. What if, let's ask this question. What if 10 years passes? Let's plug in the number 10 and see what happens to this 10,000. We are putting in 10 now for our power, right? And there it is, goes in that spot up there. Okay, break out the calculator, punch it in, here we go. 10,000. It's like we're multiplying the 0.88 10 times, basically. Our 10,000 goes down to 2,785.01, round to the nearest tenth, right? Okay, let's put that in. How are we doing out there? Okay, so this gives me, I'll do approximate here, 2,785.01, yay. You guys ready for the last one? Okay, here we go. Word problem. What is the difference in the value after 10 years of an initial investment of $2,000 at 5% annual interest when the interest is compounded quarterly rather than annually. Quarterly is n equals 4. Annually is kind of boring. So what I'm going to do is I'm going to go ahead and make that a different calculation. We'll call it weekly. How about that one? We haven't heard weekly in a while. Weekly means the number of weeks in a year, and equals 52. Okay, we're going to do this problem twice. Here's our function. A equals P times 1 plus R over N to the NT power. Let's plug the numbers in. We're looking at $2,000. And 1 plus 5%. We've got to convert that 5%, don't we? 5% is 0.05 when you move it 2 spaces to the left. Yeah, let's put that in. And in our first calculation, divide by 4. To the 4 times, what are you doing this? 10 years, okay. I wish I'd pick something else more interesting besides just 10 years all the time. Okay, we'll punch that in a second. And let's set up this other one. $2,000 still. 5% converted to a decimal, divide by 52 this time. Is it going to be a lot of money? What's a fraction? Still a fraction. That's a fraction now. They were breaking that up, okay? To the 52 times 10. Okay. We'll punch both of those into the calculator and see what we get. Here we go. Dun, 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 dun. Share calculator. Here we go. All right, $2,000 times 1 plus 0.05 divided by 4 quarterly to the power of 4 times 10. I mean, you can put in 40 if you want to. I'm being very literal. Whoa! Okay, let's write that down. $3,287.24. Yay. Let's write that down. Good amount of money there. How much more is the other one is the question, yeah? Okay, let's punch in the other one. Thanks for hanging in there. Good job. All right, last problem, $2,000 times 1 plus 0.05 divided by 52 this time. To the power of 52 times 10. This is going to be a lot of money. Well, a few more dollars. Yeah, disappointing. Huh? $9 more maybe? $9 and yeah, how much more? Let's write this down. $3,296.65. Okay, not much. Yay, thank you very much. Let me know if you have any questions. If I don't see you, have a good day. Bye-bye.